For the past 9 minutes, the space shuttle has been powering through the atmosphere, pushed forward by 2 massive solid rocket boosters. These boosters completed their job just 2 minutes into the flight and are now falling back to Earth, where they will be recovered, refurbished, and reused. The final push to orbit comes from the orbiter's 3 main engines, which are fed liquid oxygen and liquid hydrogen from the colossal orange external tank at an astonishing rate. After draining its 700 tons of fuel and oxidizer, the time comes to shut down the main engines and jettison the external tank. Inside the orbiter, the astronauts transition from a roaring, vibrating ride to serene silence, becoming weightless the instant the engines power down. The light of Earth's blue curve floods through the windows, the journey to orbit complete, but the mission only just beginning. The space shuttle was more than a rocket. It was a mobile laboratory, a home in space, and a workshop equipped for complex tasks in orbit. It provided a safe haven with a breathable atmosphere, precision maneuvering systems, and a payload bay large enough to carry massive spacecraft like the Hubble Space Telescope and the tools needed to repair them. Once in orbit, the orbiter releases the external tank, which re-enters the atmosphere and disintegrates. Photos of the tank are taken to check for any issues from launch, and to do this, the commander must pitch the shuttle onto its back using the reaction control system. Scattered around the orbiter are smaller rocket nozzles, including those in the forward reaction control system, a removable module in the nose, containing 2 spherical tanks, one filled with nitrogen tetroxide oxidizer, the other with monomethylhydrazine fuel. These fuels are hypergolic, igniting instantly upon contact without an ignition source, but they are also highly toxic, producing orange clouds of dangerous gas. Breathing it in can cause the lungs to fill with fluid and interfere with the blood's ability to carry oxygen, so ground crews wear pressurized suits and astronauts keep safe distances from these thrusters during spacewalks. Despite their hazards, hypergolic fuels are extremely reliable, storable for long periods, and ideal for precise, instantaneous thrust control. The propellants are pushed into the combustion chamber using high-pressure helium stored in spherical, Kevlar composite tanks with titanium liners, each just 10 kilograms in weight but half a meter in diameter. The forward reaction control pod contains 12 thrusters, each producing 3,870 newtons of thrust, while another 24 are located in rear pods. For fine control during docking, 6 smaller vernier thrusters produce only 111 newtons of thrust, enough to lift an 11-kilogram weight on Earth. Astronauts control these thrusters from the commander's seat on the left side of the cockpit and from the aft flight deck, which allows visibility through rear windows for rendezvous or payload operations. Each station has a square knob controller for translation and a traditional stick for attitude control. Commands go through the shuttle's flight computers, which determine the optimal firing sequence. One exception to this fly-by-wire system is the landing gear, lowered mechanically to avoid accidental deployment from a cosmic ray-induced computer glitch. At low altitude, the pilot flips protective covers to arm and lower the gear, releasing a hydraulic actuator that lets them drop into place. On the first day in orbit, the crew begins working toward their target, perhaps a rendezvous with a satellite like Intelsat. Through the forward windows, a bright dot grows slowly closer. Additional overhead and rear windows give views into the payload bay. These windows had to survive both debris impacts and re-entry heat. Each consists of multiple layers, a 15.7 millimeter aluminosilicate pressure pane, a similar thickness thermal pane able to withstand 482 degrees Celsius, and a 33 millimeter fused silica center pane as a fail-safe. Only the rear payload bay windows lack thermal panes. Below the crew deck, the middeck houses science experiments and sleeping stations. Astronauts can strap themselves to walls or ceilings inside lightweight sleeping bags fixed with Velcro. Some, like Story Musgrave, preferred to free float, though that risked bumping into crewmates. Soon after reaching orbit, the payload bay doors must be opened to expose radiator panels on the inside, part of the thermal control system. Coolant-filled tubes carry heat from inside the orbiter to these radiators, where it is shed into space. The doors are made from graphite epoxy composites, reducing weight by 48 kilograms compared to aluminum designs. The bay is 18.3 meters long and 4.6 meters wide, capable of carrying payloads up to 22.7 tons. During mission STS-93, a gold pin used to plug a damaged oxygen post in an engine injector came loose during startup, striking hydrogen coolant channels and causing a leak. The engine responded to the resulting drop in chamber pressure by adjusting its oxidizer valve, unknowingly making the problem worse. The mission succeeded despite an early shutdown, but the incident led to a new policy. Damaged injector posts must be replaced, not plugged. If the orbiter falls short of its planned velocity, it can use its orbital maneuvering system, powered by the same hypergolic fuels as the RCS, but in larger engines capable of adding 305 meters per second of speed. For precise navigation, the shuttle uses star tracker optics behind doors in its nose, matching known star positions to determine its location in space. On STS-49, the mission was to capture and repair a stranded communications satellite. Astronauts Pierre Thout and Richard Heeb suited up for an EVA, planning to use a capture bar to stabilize and secure the satellite. Multiple attempts failed, the bar bounced off each time, but engineers on the ground could restabilize the satellite for another try. After 2 days of unsuccessful attempts, the crew considered a bold new plan: send out 3 astronauts instead of 2, with 2 grabbing the satellite by hand while the third attached the capture bar. The Middick airlock was designed for 2 people and had only 2 life support umbilicals, so the third astronaut, Tom Akers, had to operate on his suit's internal systems. Squeezed into the cylindrical airlock, he floated in upside down while Thout and Heeb stood upright. After depressurization, all 3 floated outside. Inside, Bruce Melnick operated the shuttle's robotic canadarm. His background as a Coast Guard helicopter pilot made him ideal for this task, as controlling the arm required similar coordination to controllers for translation and rotation, much like a helicopter's cyclic and collective. The canadarm, 15 meters long and weighing just 430 kilograms, could move 30 tons in orbit but couldn't support its own weight on Earth. With 6 joints and an offset elbow allowing 160 of movement, it was built for delicate work and weightlessness, where even a small force could move large masses. Since the satellite had no grapple fixtures, the capture bar included one, allowing the arm to secure it. The end effector used 3 motorized wires to snare a pin and lock it into place. Once the satellite was secured, the new rocket motor was attached, enabling it to boost itself into geostationary orbit, where it operated for 21 more years. Life support aboard the shuttle relied on high-pressure oxygen and nitrogen tanks to maintain an 80/20ths atmosphere, with lithium hydroxide canisters removing carbon dioxide. These were replaced every 12 hours. The orbiter's fuel cells combined hydrogen and oxygen to produce electricity and water, the latter degassed before use to remove dissolved hydrogen. On STS-49, closing the payload bay doors before re-entry proved tricky due to thermal warping. The crew put the shuttle into barbecue mode, slowly rotating to equalize temperatures, and after an orbit the doors latched successfully. For re-entry, the orbiter fires its OMS engines to slow down. Entering the atmosphere at 7 to 8 kilometers per second, about 30 times the speed of sound the shuttle experiences. Intense heating as air molecules are ripped apart, forming a plasma sheath around its underside. Peak temperatures reach about 1650 degrees Celsius. Surviving this while transitioning into an unpowered glider capable of landing on a runway demanded some of the most innovative aerospace engineering ever achieved. The space shuttle was truly a spaceplane, bridging the worlds of rocketry and aviation in a way no other spacecraft has matched.